Hey everyone, it's me, Miss B, and in today's video, we are looking at the Unit 4, Lesson 5, Cumulative Practice Problems. And this is from Illustrative Math Geometry. So for this lesson, we're going to need to use our um, table of ratios. So I actually have it as a little sticker thing that I can add to this and move around. I'm going to zoom in and use it in different places here, but you may just see me move this little sticker around with me or delete it as needed, just to reference these things. So we have our adjacent and hypotenuse, opposite and hypotenuse, and opposite adjacent ratios for all of the angles in increments of 10 through 80. So things that we might find in our right triangle. So for right now, let's actually get this guy out of here. Whoops, could use my pen for that. So we'll delete that. And let's look at our first question. So we have a triangle with side lengths 8, 15, and 17. We want to do two things. Verify it's a Pythagorean triple and then approximate the acute angles in this triangle. So I'm going to draw mine first. That is a poor looking triangle. But maybe, there we go. And right about there, that should be a right angle. And I'm going to say that this bottom part is 8, 15 is the right-hand side, and 17 is the longest one, so it needs to be the hypotenuse. So let's verify this is a triple. So I'll zoom in here and do a little bit of this work. Basically, we're going to say 8 squared plus 15 squared should equal 17 squared, and we're just going to confirm that. So with 8 squared, we get 64. And with 15 squared, we get 225. And with 17 squared, we get 289. And if you take 64 plus 225, you get 289. So we have 289 equal to 289. So it is actually a Pythagorean triple. Now we want to approximate the acute angles in this triangle, and that's what we're going to do using our table. So if I approximate 1, I can then use the triangle angle sum theorem, which says that all of them should add up to 180 to find the other. Because basically these are all going to be complementary. So I'm going to start, and I like to, just when I am trying to identify angles, I like to use the one that is like along the base that's at the bottom. So in this case, I'm going to use the one down here. Now we can't use the right angle. We have to use this one here. Now I didn't label anything here, but I am just going to label this as, we'll label this as theta, because I'm not sure what that angle is to start with, but just to mark that that's the angle that I'm using. And so let's use adjacent. I'm going to use adjacent over hypotenuse, but let's label all of our pieces here. Adjacent should be the one right next to the angle, the one that's not the hypotenuse. So you'll technically have two that are right next to your angle and one that's across. 17 is always going to be the hypotenuse, but the leg that is right next to your angle, that's going to be your adjacent. So the angle is always formed by the hypotenuse and the adjacent leg. They make up that actual spot where the angle meets. So that makes 15 our opposite, and 17 is the hypotenuse. I tend to use these three-letter abbreviations just because I don't like to use single-letter abbreviations like H, O, and A, because then sometimes those get mistaken for variables. So I'm going to actually plug into a calculator here and do adjacent divided by, so I'll do adjacent over hypotenuse, and that is going to be 8 over 17. So 8 divided by 17, and we're going to round this to 3 decimal places. I'm showing on my calculator it is 0.471 because it's 4705, but that 5 means we bump it up 1. So now this is where the table comes into effect. So let me get my, oh, large table here. I'm zoomed in, forgot about that. It's a pretty big one. Okay. So I'm going to try to compare that 471 to anything in my adjacent over hypotenuse column. And I don't see anything matching it exactly. I have 342 and I have 0.5. One of these is smaller and one of these is bigger. So that tells me this is probably going to land somewhere in between those two things. So let me actually grab this and I'm going to make it a little smaller and kind of scoot it to the side. I want to show some of my stuff here and I'm going to delete my little table afterwards. So let's say angle theta, that's going to be 3, 4, 4, 7. It's pretty close to 60, but so I might call it like 63. Because if you look, it's 0.47, and that's pretty close to 5. So I'm going to call it just a little bit above that one. So I would say this is between 60 and 70 degrees, and I might say that the measure of angle theta is approximately, I don't know why I put approximately and then an equal sign, 63 degrees. So let's call this other angle, yeah, I don't know of another good Greek letter to call it. We can maybe call it mu. I just don't like to use Greek letters that are actually meant to mean something else. Um, so actually, here we go. I know. Now that I have one, I can just approximate and say that they are 63. And I can say other angle is approximately. And in this case, they need to add up to 90, so that's going to be about 27 degrees. We can actually take our other angle, though, and look at what that would have for adjacent over hypotenuse. If we used our other position, this would now become our adjacent, and this is our hypotenuse. So if we did 15 divided by 17 and then cross-referenced with our tables, let me get that table back. So 15 divided by 17, and we want that to be around 27, so pretty close to 30. 15 divided by 17, 0.882. And if I take a look here at 30, 30 is 8, 6. And to get higher up would be closer to 20, so 0.88. That would work for us saying that this is 27. That would be correct, that it falls within that range. So I think we're safe to just leave it at that, using this as the idea that like this is 90. I would say that this is like 90 minus the 63 is where I got this number from. And that one's fine. So that then brings us to question 2, where they drew something for us. We didn't have to draw it ourselves. Kieran is flying a kite. He gets tired, so he stakes the kite into the ground, and the kite is on a string that is 18 feet long and makes a 30-degree angle with the ground. How high is the kite? So I'm going to label what they want us to find here as X, and that is the height. It's the vertical leg there, and so that's what they want us to find. We are again going to reference our table, but what we have here is the opposite and the hypotenuse. Now we don't actually have the opposite side, but we do have the fact that we need that side. So what we can say is with our 30-degree angle is that here we should have the opposite over the hypotenuse should be equal to x over 18. And so this is the 30 degrees opposite over hypotenuse. So we're going to find that on our table. Bring back my giant table. Opposite over hypotenuse, I can see right here, it is 0.5. So I'm going to move this thing out of my way. Oh, I just grabbed everything underneath it. Okay, so since it's 0.5, I can say 0.500 should be equal to x over 18. Multiply both sides by 18, and then we are done. So if you multiply here by 18 on both sides, you actually get that x is equal to 9. And so our answer would be 9, or 9 feet off the ground. Now, if you recognize this was a 30-degree angle, so you had a 30, 60, 90 triangle, you could also do that. But since they gave us a perfect tens, multiple of 10, I figured we would use this opportunity to show you how the chart works. But this, and conveniently I did label it x, this then side, the hypotenuse should be 2x, and the long leg would be x times the square root of 3. So it does work that way as well. And if you recognize that, you could take that 2x is equal to 18, so 1x should be 9, and you'd arrive at the same answer. Let's look at question 3. Triangle ABC has a right angle at C. Okay, I see that's marked for us. We want to select all measurements, which would mean it has a hypotenuse with a length of 10. So we want it to have a hypotenuse of 10. And we have a couple different things here that we can try. So angle A is 20 degrees and BC is 2. I don't, oh, you know what? I do see one first that we could test, because I see this one is 30 degrees. And just like I said on the previous one with a 30, 60, 90, we could actually test that this is true. So for the blue part, it says that if angle A is 30 and BC is 5, then yes, this actually would work, because we should have x, 2x, and x root 3. So the short leg, or BC, should be half the length of the hypotenuse. So that one actually does work, and we can do that just using those relationships. So let's select that one first. But now we have to kind of measure everything else out. So if A is 20 and BC is 2. So looking at our table, I'm not going to keep bringing the table up on here because it is rather large, but you can reference that same table, or you can just trust me with what I am referring to, but you do need that table to do your homework. So if A is 20 and BC is 2, let's try with that. Now, looking at 20, we have the hypotenuse here as 10. 10 is always going to be the hypotenuse. We want to know, in this case, we have 20 degrees, and then we have the opposite in the hypotenuse. So opposite over hypotenuse for 20 degrees, that should be 0.342. And is 0.342 the same as 2 over 10? And the answer to that is no. 2 over 10 is the same as 1/5, or just 0.2, so it doesn't work. But that's how we can eliminate choices. So let's continue, and we're going to use the same ideas and go along with it. So AC is 7 and BC is 3. We can check using the Pythagorean theorem for this one, but these ones will not work, because 7 plus 3 is 10, and the hypotenuse has to be longer than either of the two put together. But just for your, just to prove this mathematically, 3 squared plus 7 squared is that equal to 10 squared? It's not going to be equal to, because 9 and 49 does not make 100. So we can cancel out B as well. Okay, angle B is 50 and BC is 4. That's our next one. So I'm going to erase what I've got here. Angle B is 50 and BC is 4. I'm going to use my table and refer to that on this one. So in this case, from angle B, 4 is my adjacent. So I'm going to have adjacent over hypotenuse. And my adjacent over hypotenuse for this one, for 50 degrees, should equal to adjacent over hypotenuse 0.643. Oops, sorry, I'm right next to the wrong one. 0.643. And we want to know, is that the same as 4 over 10? No, 4 over 10 is 0.4. So that one should not work either. That leaves us one last one. AC is 8 and BC is 6. And so we want to check if that one works. And since they're giving us all measurements here of the sides and no angles, that means we can use Pythagorean theorem. So AC is 8 and 6. 6 squared plus 8 squared. Is that equal to 10 squared? The answer to this is going to be yes, it is, because this is 36 plus 64 equals 100, which it is equal to 100. So D and E are the only acceptable answers here. And okay, so I'm going to erase just those couple little markings and let's look at question 4. Now, question 4 is something we can just use our table for. It wants to know a reasonable approximation for an angle B, and then it gives us the ratio of the adjacent leg over the hypotenuse. So adjacent leg over hypotenuse, that's the first column on our table. And we're going to try to find what is close to 0.45. Now, I have 4 adjacent divided by hypotenuse. I have a couple angle measurements here that it's kind of close to, and for what it's actually going to be like in between. I have 0.5 for adjacent over hypotenuse, and that's 60 degrees. I'll just put degrees here since I'm making a little table out of it. And then at 70, I have 0.342. So 0.45 would be in between there somewhere. So it's going to be between 60 degrees and 70 degrees. So we know it's not 27 or 30. If you're looking at this and you're like, well, 60, it could be, or 63, it's not going to be 60. If it was 60 exactly, we should get exactly the 0.5 ratio. And since we don't get 0.5 exactly, that means it's not between those or equal to them. It is literally a number that has to be somewhere in between those. So 60 is not correct, and it's going to be D, which is 63 degrees. So that's going to bring us to the backside of our homework. So let's look at this one. This is going to be estimating values to complete the table. Well, if it wants us to estimate, lucky for me, I know that there's a trick to this. And because we don't have angles to go from, we have to go with patterns on our table. So what we know is that adjacent and opposite switch when we change angle. So that means we are essentially going to have these boxes here trading places for the other angle. So here I should have 0.95 because the adjacent for this one is the opposite of the other angle, and this should be 0.31. For the same reason, the opposite of angle C, is going to be AB, and AB would be adjacent to angle A. Now, the opposite divided by adjacent leg column, this one's a little trickier. This one is the reciprocal. Now, most people know that the reciprocal is a fraction that has just been flipped. But anytime they give you a number, even if it's not a whole number, and this one's a decimal, if they just give you a decimal, you're essentially treating that as like a number over 1. So what we're going to do is do the reciprocal of that because we are trading opposite and adjacent places. This is now going to become 1 over 3.1, and we're going to give the decimal approximation of that. So we're going to use a calculator. 1 divided by 3.1, and I'm going to round it to 3 decimal places. So 0.323. Now, everything else here, they were using 2 decimals or just 2 digits. That's fine. I just like to round to 3. But if they only wanted you to round to 2, you would just ignore the last digit here and just call it 0.32. That brings us to question 6. So what is the length of side AB? So we want to find AB. We know that this length is 6, and this is 30 degrees. Instead of using our triangle ratio table for this, I'm just going to use what I know about 30, 60, 90 triangles. So I know that the short leg, or the one that's opposite from the 30-degree angle, I'm going to call that x. The hypotenuse is twice that length, and the long leg is equivalent to x times the square root of 3. And since I have a number here, I'm going to put that the 6 is equal to x root 3. So in order to find AB, that is this one right here. So I'm just going to try to find x. So I'm going to take this here and divide both sides by the square root of 3 and show my work this way. So these will disappear or cancel out with each other. And I have to multiply by root 3 and root 3, top and bottom here. So we're going to end up with x equals, I'm just going to show that I'm bringing my work up here, 6 root 3 over 3. So x is really equal to 2 square root 3. So I will say AB equals 2 root 3. And I know that when we do the homework check or quizzes on these, they don't actually give you the option to really put the roots in for some. So let's actually give a decimal approximation for this too, especially if you just did it the decimal way, or you used the table. That would give you one of these answers too. So I'm just going to multiply out 2 times, let's do the square root of 3, and we're going to multiply that by 2. I'm going to say it's approximately 3.464. Now, the number after that is a 1, so we're pretty safe to leave it at that. And if you need 2 decimals after, you can see that I have the third one there, so you can always reduce. Okay, question 7 and then question 8, and then we're done. So 7 says, what is the length of the square's side and how do you know? Now there is a little trick to this one. And if you remember what the trick is, it's pretty easy and you don't actually have to use any math to be able to do this one. But I think they have it labeled a little funky in here. I would not leave this answer the way they have it written, because the answer here is 6 divided by square root of 2. And yeah, that's true, because for a square, we would have x, and x root 2. So we would want to take each piece and divide them by the square root of 2 to just get our side length. But I wouldn't leave it as 6 divided by square root 2. We would actually rationalize our denominator, and this would end up, the simplified version is what I meant, the pattern kind of shows up as. So since we're doing the same pattern here every time, if that's an even number, we're just going to divide that number by 2, and actually put a square root next to it. So this would be 3 square root of 2. Those would be the same thing. I would prefer to leave it as 3 root 2, but they're giving it to you as 6 divided by root 2. So last question, number 8, find all the lengths of segments AD and BD, then check your answers using a different method and show all your work. So we have AD and BD. So I'm going to call BD H, because this looks like a geometric mean question to me. I'm going to call AD Y. So first thing I can do is I'm going to find H just by doing the Pythagorean theorem. And if you notice, this one has a specific pattern to it, you can probably jump right to it without doing the Pythagorean theorem, but I'll show the whole Pythagorean theorem, because I'm not going to make assumptions that we just know how to do it. If you divide that, or I'm sorry, if you subtract that 144 from both sides, you'll get 25. And so the value of h when we take the square root of both sides is 5. This is a 5, 12, 13 right triangle. So if that's 5, I can now find y by doing the geometric mean. So just as a refresh on geometric mean, either the altitude or the legs of the large right triangle, those will be your geometric mean, or the things we would use as geometric mean. I would call this side B and this side A. A, B, and H would all potentially be the geometric mean. The remaining pieces that we have are Y and X, and then I would call the entire distance here C. We are only going to use 2 of those, and based on whichever variable or length that we have here, and in this case I'm going to use the 5 and the 12. So this geometric mean here, it touches the endpoints of 2 of these sections because it ends right here, so it touches Y and it touches X. That's how I know it's going to be the geometric mean of those 2. If I was using A touches the endpoint right here, which touches 12 and C. So that's a long explanation, but just to give you a little refresh at least, I'm going to show some of my work here and say that in order to find y, I'm going to set up geometric mean. That is going to be h, or 5 in this case. When I set up a geometric mean, I know it should be across from itself on a proportion like this. And then my other 2 spaces, it doesn't matter which one is which, but those are going to be my other 2 numbers. So one of these is going to be y, and the other one is going to be 12. So cross multiply, we would end up with 12y is equal to 25, and we would divide both sides by 12 and get that y is equal to, it's not going to reduce nicely, so let's just grab what our decimal approximation is. This is about 2, like you could leave it as 25 over 12. I'm going to say 25 over 12, or 2.083, and the 3 repeats to infinity. So how can we check both of these values? Okay, so I paused and took a look at it, and I don't think there's really a way that I can check this without using instead like the entire length here of C, or like this side, and like incorporating like this value into that. So we're just gonna leave this here, and we're gonna call our answers here 5. And if you wanted to round this to just a smaller number, you could also call this 2.1. I believe that's what the book also calls it. But I like to leave a couple varieties, so that's what I'm going to leave you with, because this video is already long enough, so you do not need to see me do the very long check step here for this, and this part was why, sorry. So thank you for sticking with me through this, and yeah, I will see you in the next video. This has been the Unit 4, Lesson 5 Cumulative Practice Problems for Illustrative Math Geometry.